Hey guy, welcome back to my YouTube channel, the one and only YouTube channel on YouTube. So I just want to thank you guys for 100 million subs. It's been my dream since yesterday to hit that goal, and I'm really proud that we got there. Okay, so today I'm going to be talking about a phenomenon called Benford's Law. All right, if this spotlight thing on my cursor is bothering you or anything, just tell me and I'll get rid of it right away. All right. Okay. So here we go. Let's just jump right into it. And it's gone. Okay. All right. So no spotlight thingy. Oh no. Oh yeah. Okay. Oh yeah. It's all coming together. Okay. All right. So let's say we had for example, let's say we had a data set with n amount of numbers. So how often do you think that the numbers in this data would start with a 1? How often do you think they would start with a 2? And how often do you think they would start with 3, etc., until they started with a 9? So you would suppose that since there's an equal likelihood of each digit appearing, that there should be a 1 in 9 chance of each leading digit to be a 1, a 2, or 3, all the way up to a 9, right? So if you had a number such as 356, the leading digit would be a 3, right? So if you have a data set with all of these numbers, how often would the leading digit 1 or 2 or 3 appear? So it should, you think it would look something like this in this graph right here, where everything's kind of even. It's, not perfectly even, but it's around 1/9 for each leading digit. But in reality, due to the thing I'm going to be talking about today, it's actually way different than you imagine. So it was discovered by this guy named Simon Newcomb, who was an astronomer, and he was the first to discover this phenomenon concerning leading digits. He wrote a paper on this, but this topic didn't actually gain traction until this other guy named Benford stumbled upon the same phenomenon on his own. He didn't really copy him, so don't worry about that. And so the one thing that they noticed when they were practicing, when they were, doing work in their field, was that papers at the beginning of their log tables were getting dirtier than the rest and like more worn and used. So log tables are these things where there weren't calculators back then. This was in the 19th century, so they had to use this thing called log tables. And so they had a bunch of these papers, and Newcomb and Benford realized that only the papers in the beginning were seriously used, and the papers in the end weren't being used at all. So they were a lot cleaner. And this led to this discovery of a law we now call Benford's law. Okay, so what it states is that given a set of numerical data, and there are a few catches, I'll talk about it later, but a majority of the leading numbers in the set of data will begin with 1, 2, and 3. So it's completely different than the graph that we had right here, where it's like a 1/9 chance of each leading digit appearing. Whereas in here, the leading digit of 1 has just a bit more than 30%, which is 30.1% of appearing. Leading digit of 2 is like around 17, and all the way down to 9, which is less than 5%. So it was a really astonishing and just weird phenomenon. And this graph shows the probability of obtaining each leading digit in data sets of base 10. And so the catch I'm talking about, I was referring to, is that the data set has to span across many orders of magnitude, which means if you had a number like 10, it would have an order of magnitude of 1, and 100 is 2, and 1,000 is 3. So just the larger the numbers are, the more it's going to follow this phenomenon called Benford's law. Okay, so where does Benford's law apply to? So it applies to a lot of things, actually. So it applies to even the stock market, import, export volumes of fish, and other weird stuff. you got the area of all the world countries, and it's even in miles squared, feet squared, and acres squared. But they all follow Benford's law because they're all big enough. All these numbers are big enough so that they're going to follow Benford's law. They all have orders of magnitude that exceed the necessary requirements to follow Benford's law. And it also works in star brightness and depth of earthquakes, street addresses, river length, all that, like basically anything you can think of, to be honest. So I think the easiest way to explain this is, let's say, for example, you were taking part in a raffle, and so the winner would get like a brand new Toyota Prius. So if there were 2 raffles, and so the number on the first raffle is 1, the number on the second raffle is 2, what are the odds that the winning raffle is going to begin with a leading digit of 1? Well, it's 50%, right? Because it's either 1 or 2. And so if you increase the number of raffles, so now you have 1, 2, and a 3, the chance of the winning ticket leading with a 1 is going to be 33%. 4 tickets, 25%, et cetera, until you hit 10. So when you hit 10, something changes. So the percentages keep on decreasing, right? So when you get 9 tickets, it's going to be 1/9. If you have 1 ticket or 2 tickets between 1 and 2, you're going to have 50%. But when it goes to 9 tickets, you're only going to have a 1 in 9 chance. So these probabilities keep on decreasing as the number of tickets gets greater. The probability of like the leading digit being a 1. But when you hit 10, this probability is going to get higher and higher because now all of these 10s numbers are starting with a 1. So 10 now becomes 2 out of 10, which is 20%. 11, 3 out of 11, which is something I don't know because I'm not a genius. Okay, and then it goes all the way up to 19, and then it increases all the way up to 19. And then it decreases again when it goes into 20s, 30s, 40s, etc., until you hit 100 again, where the leading digit begins with 1 once again. I'm not using my pointer. Oh my god, I'm an idiot. Okay, I'll use my pointer now. Okay, so okay. So when you hit the hundreds, the leading digit is going to start to be 1 again. So right here, you'll see that the probabilities, if there's only 1 ticket, the probability is 1 out of 1. But then you start decreasing the probabilities start decreasing all the way to 9, and then 10s, they start decreasing until 100. Then it starts increasing for however many, for infinity, as long as counting numbers exist. So this is the graph that's created out of this raffle situation. So you see that as the number of tickets increases until 10, the probability of the leading digit being a 1 decreases, and then it increases, decreases, increases, decreases, decreases, etc. Okay. And so what this says is that in a data set of a random n amount of numbers with a large amount of orders of magnitude, the distribution is going to be highly skewed towards a leading digit of 1. Because if you took the average, if you don't know how many numbers are in this, you just take the average of these, right? So it could be like 500 numbers or 360 numbers or 620 something numbers, and you take the average of this, and you'd find that the probability of having a leading digit of 1 is never going to be below 1/9. It's always going to be greater. And then if you take the average and you draw like a straight line across, the probability of getting a leading digit of 1 is around 30%. And so Benford created this equation to express this phenomenon. So it goes, the probability of a number leading with a digit is equal to base 10 of 1 plus 1 over that leading digit. So if D is equal to 1 in our situation, the probability of a number leading with the digit 1 would be base 10 of 1 plus 1 over 1, which is just log 10, base 10 of 2. And if you put that in your calculator, it's going to be 30%. Okay, and I think a more intuitive way to think about Benford's law, this one made not more sense, but I think is just an easier way to think about it. So let's say you let's take for example the Nasdaq, okay, and let's say that currently on the stock market it's worth 10,000. Um, so right now it's starting with a leading digit of one, but how could it get? Well, when would the leading digit not be one? Well, that would be when it gets to 20,000, right? But think about how many points the Nasdaq has to traverse in order to get to 20,000. It would literally have to double in order to get 20,000, and that's just not plausible, you know. But if you had, let's say, the Nasdaq was at 9,000, well then how could a leading digit of nine get to a leading digit of one? Well, it would just need to go to 10,000, but that's only an 11% increase. That's way less mileage that the 9,000 has to traverse in order to get to 10,000 compared to a 10,000 getting to 20,000. So it's just easier, and it's more probable that you're gonna find a number with a leading digit of one um, than a leading digit of nine, because it's just way harder for the leading digit of one to get to a leading digit of two. Um, and there's tons of other explanations, but I don't understand them because I'm dumb and I just don't want to explain them. Yeah, okay. Okay. So some really cool stuff is that Benford's law even works with the Fibonacci sequence and almost any power, and the powers of almost any number, which is I think really cool because, um, yeah, I don't know, the Fibonacci sequence just seems like something that should work, or I guess is mathematically sound, but it still follows this law for some reason. And so we can also find the probability of a second digit being a certain number, which is in the graph to the right, um, where you see that the probability of having a second digit in zero is 12%, and it goes all the way down to 9. And it's like the same kind of trend that we saw with the distribution of the first digit. It's not as extreme, but it's definitely noticeable. And some applications are that it's mainly incorporated into fraud and corruption detection. So forensic accounting and auditing, when determining accounting and expense fraud. So it's known that people who kind of forge or falsify their tax records are going to be people who like usually choose numbers that are more uniform. You know, so more like shit, more like oh shit, more like the graph we saw here, where each number, each leading digit had more of it, had like around a 1/9 chance of occurring. But in reality, according to Benford's law, it should look something like this, where ones are appearing way more. And that makes sense because in given like huge orders of magnitude in like the millions, you wouldn't it would make sense to find more stuff, more numbers that begin with one than like nine, due to the same logic I'd applied to like the Nasdaq. So yeah, it was also used in the Iranian election of 2009, and it showed that tampering was evident due to its deviation from Benford's law. And yeah, I think it's just a really cool way to apply this seemingly useless phenomenon. Yeah, and apparently Iran wants to boycott phony pea honey. All right, whatever. All right, thank you. Peace. Remember to like, subscribe, comment, and share. We're doing a giveaway. I'm giving away Davies used underwear. If you want to be a part of this raffle, just comment down below with a number, and I'll choose one, and we'll see who gets that used underwear. It could be you. Peace.